Good morning, students. In the last class, we started a new chapter, Chapter 5, Electromagnetic Induction and Alternating Currents. And we also see that it's very important because it's due to electromagnetic induction that we can now enjoy electricity, and also it's available everywhere. It's easy for distribution and production. And we saw in the last class the experiments conducted by Michael Faraday, which led to the discovery of this phenomena, that is electromagnetic induction. Now today, we want to discuss the laws of electromagnetic induction, but before that, we have to be introduced to a new quantity called magnetic flux. So first, we will see what is magnetic flux, and then we will continue with the laws of electromagnetic induction. There are three laws of electromagnetic induction. Two of them are by Michael Faraday, and the third one is by Lenz. So let me share my screen with you. Can you see the screen now?
Yes, teacher.
Okay. So today we are going to discuss first what is meant by magnetic flux. I hope you have already learned in electrostatics what is electric flux. Do you remember that? Electric flux, which was represented by phi E. Electric flux was the product of electric field and the perpendicular area through which it passes. So it was defined as phi is equal to E dot A. Now, similar quantity is magnetic flux, and magnetic flux is defined as the product of the magnetic field and the perpendicular area through which it penetrates. So it's a scalar quantity. We know that magnetic field is a vector quantity. And area, I told you before in the last chapter that sometimes we take area as a vector. And suppose this is a surface, we are taking the area of this surface, then the magnitude of the surface will be the magnitude of the area vector, and the direction of the vector will be perpendicular to it in this direction. So magnetic flux is the product of two vector quantities. Magnetic field is a vector and area is also a vector. So in order to get a scalar quantity with two vector quantities, how should we multiply them? You have learned two types of multiplication for vectors. There are two
Dot
ways.
cross product.
Yeah. Which product?
Cross.
When you cross product, when you take cross product of two vectors, what about the result? It will be also a vector. But magnetic flux is a scalar quantity. So what
You
product?
have to do in dot product. Okay.
We have to take the scalar product or the dot product. So magnetic flux is
Teacher,
defined. Yes.
what is magnetic flux?
Magnetic flux is a quantity which is defined as the product of magnetic field and the perpendicular area. And it is denoted by phi B, phi or just phi. So phi B denotes it is magnetic flux. And phi
Teacher, what
B,
are the two
yes.
vector quantities?
What are vector quantities? What did you
No,
ask?
what are the two vector quantities? The product of two vector quantities that made magnetic flux, area and direction.
Magnetic field B is a vector quantity. We have already learned magnetic field B, which is a vector quantity. We find the direction of magnetic field using thumb hand rule and all. So it's a vector quantity. It has a magnitude and direction. And another vector quantity is the area. So magnetic flux is the product of two vector quantities. One is magnetic field represented by B, and the second one is area, which is always taken as perpendicular to the surface area. So it's a scalar quantity, so you have to take the dot product of these two vectors. B is the magnetic field and A is the area vector. Is that clear now?
Yes.
Yes.
And it is denoted by phi. Phi is the symbol denoting magnetic flux. So mathematically, we can say that phi B is equal to B dot A. What is B dot A? BA cos theta, or AB is more familiar than BA, right? You can also tell it as AB cos theta. I like to remember it as AB cos theta. So theta is the angle between magnetic field B and area vector A. So what is its SI unit? Its SI unit is Weber. Remember, when we discuss magnetic field B, we told it has one SI unit Tesla and also Weber per meter square. Because when we take area to the other side, it will become divided by meter square. So Weber per meter square.
Teacher,
Yes.
why this is a dot product?
Because magnetic flux is a scalar quantity. You can get a scalar quantity by multiplying two vectors only by taking their dot product.
Yes. Okay. By multiplying two vector. I remember now. Thank you.
Okay, so that's why we have to take the dot product. So BA cos theta. And the unit of magnetic flux is Weber, which is having a symbol WB. And 1 Weber means 1 Tesla times 1 meter square, where Tesla is the unit of magnetic field and meter square is the unit of area. So the SI unit of magnetic field, we have already learned it as Tesla and area is meter square. So another unit for magnetic flux is Maxwell. And 1 Weber means 10 raised to 8 Maxwell. So sometimes if the magnetic flux is given in Maxwell, you will have to convert it to Weber. How will you convert? You have to divide it by 10 raised to 8, or you have to multiply it by 10 raised to minus 8. So where theta is the angle between the magnetic field and area vector. So phi B is also BA cos theta. It is better to remember this formula that phi B is equal to AB cos theta, so that you will not forget to take cos theta. Is that clear?
Yes, teacher.
Yes, teacher.
So the direction of area vector is always normal to the surface. So case 1, when the angle between the area vector and the magnetic field is 90 degree, what is cos 90? 0. So what will be the flux? Flux will be
0.
0. So here this is a situation. This diagram is two-dimensional, so it may not be clear to you. Here, the angle between the area and magnetic field is 90 degree. Suppose you have magnetic field lines going like this, and I keep the magnetic field is going like this towards the right, and I keep the plane or the coil of wire through which we want to find the magnetic flux like this. See, the magnetic field is going to the right, and what is the direction of area? Perpendicular, so coming out. So what is the angle between the magnetic field and the perpendicular area? 90 degree, because it is normal to the surface, right? So it is 90 degree and cos 90 is 0. So no flux is going through this surface. If this was a coil, no flux is going through this surface if the angle between the magnetic flux and normal to the
Teacher,
area is 90. Yes.
teacher, can I ask something? Where is magnetic flux used in the practical life?
Magnetic flux, we are going to learn the law of electromagnetic induction, right?
Yes.
So before that, we are learning this concept, and the next screen, I will show you practically what is the meaning of flux.
Okay.
Okay, so just mathematically, we are learning this formula now. And in the next slide, I will show you what exactly is meant by magnetic flux. What is its relevance in practical life? So here you remember this formula, phi b is equal to BA cos theta. Now case 2, when the angle between the area vector and the magnetic field is 0 degree, then what is cos 0? 1. So the magnetic flux is equal to AB. That's it. Cos theta is 1. So here, when the angle between the area vector and magnetic field is 0, that is, suppose I keep the surface or the coil in this direction. The magnetic field is going like this. So all the magnetic field lines will pass through the surface, right? And what will be the angle of the magnetic field, which is in this direction, and the area vector is perpendicular, so it's in the same direction as the magnetic field. Therefore the angle between them will be 0. All the field lines will be going through this area, and the magnetic flux is maximum. So this is case 2. Now let us see some more detail, as Irfan asked, what is practically magnetic flux? Here you can see 2 bar magnets. What are these lines called?
Magnetic field.
Magnetic field lines. They represent field lines, right? So magnetic flux linked with a coil is 10 Tesla or 10 Weber it should be. So magnetic, I'm sorry, it should be 10 Weber because magnetic flux is measured in Weber, right? So the magnetic flux linked with a coil is 10 Weber, means if the area of the coil is 1 meter square, the component of magnetic field normal to the surface of the coil is 10 Tesla. You may get similar questions. What is the meaning of magnetic flux is 5 Weber? Can you tell Muhammad Zaman what is the meaning when the magnetic flux is 5 Weber?
If the area of the coil is 1 meter square, then the component of magnetic field normal to the surface of the coil is 5
5
Tesla.
Tesla. So similar questions may be there for the exam. Now, magnetic field lines, you have already learned the magnetic field lines, right? Magnetic field lines are those lines along which when a charge moves, whatever velocity it has does not experience any magnetic force. Can you tell me why, if a charge particle is moving along this line, it will not experience any force? That is what, that is how magnetic field lines are defined. Can you explain why it is so?
Because it is inside the magnetic field.
It's not inside.
I mean, no other force is
On the
acting.
Oh, magnetic force should act, right? It's not acting. Even magnetic force is not acting if a charged particle moves along this line. Can you tell me
Then
why?
Vijay, can you
can you
repeat
say
the
the
question?
question?
The question is that when a charged particle is moving along this line, that is along the line of the magnetic field, then no force will act on that charged particle. No magnetic force will act on that charged particle. Why?
It's out of the magnetic field.
No, it's not out of the magnetic field. What is the force acting on a charged particle moving in a magnetic field? F is equal to
UV sin theta.
QVB sin.
BB sin theta. Sorry.
Okay, So if the charged particle is moving along this line, what is the direction of its velocity? Same as the direction of the magnetic field, right? So what will be the angle theta that is between the velocity and magnetic field?
0.
0. So what will be the force acting?
0.
0. Sine 0 is 0.
Yes.
Is that clear? So
Yes, clear.
this direction is the
I
direction.
didn't understand.
See, if a charged particle is moving along this line, it means that the velocity of the particle is in this direction. And the magnetic field also is in this direction. So what is the angle between the velocity and magnetic field? They are in the same direction. So what is the angle, Irfan?
It's 0.
0. What is sine 0?
And 0 is 0.
0. What is the force acting on a charged particle? You already learned that in the previous chapter.
Yeah. A Q, I think.
Be sine
Sin
theta.
theta.
So that
Q,
theta will become 0, sine theta will become 0. So the force acting on it will be 0. Is that clear to you now?
Yes. So this teacher is just mathematically proven, right? That it is 0.
Yeah.
So in practical life there will be any force?
There may be gravitational force. That's all. Magnetic force
Yeah,
will not be.
that's it.
So the magnetic field lines are those lines along which when a charge moves, whatever velocity it has, does not experience any magnetic force. See, they have particularly told magnetic force will not be there. So those lines are called magnetic field lines. Now, in a place where magnetic field lines are closer, the magnetic field is stronger. You know that, right? And in a place where the magnetic field lines are farther away, the magnetic field is weaker. So look here. Look here. I mentioned this as place A and this as place B. Where will be the magnetic field more? In place A or place B?
A.
A, because the magnetic field lines are close together there compared to the place B. Now here, look at this position here. Let this be place C and this be place D. So where the magnetic field will be more, place C or place D?
C.
Where the magnetic field will be more, at place C or place D?
Place C.
Place C, why? The magnetic field lines are closer as shown here, because the magnetic field lines will always be directed from the North Pole to South Pole. So from North Pole, they are going away because this is repulsion of two like poles and this is attraction. So it goes from North to South Pole, this direction. So this is just to show you what are magnetic field lines. And now the relation between magnetic field lines and magnetic flux. If a coil of wire is placed in a place where the magnetic field exists, the number of field lines passing through the coil is called magnetic flux linked with the coil. So if there are more field lines passing, then what will we say? The magnetic flux is more. Okay. So if there are more
So what
field,
you said?
if a coil of wire is placed in a place where the magnetic field exists, suppose here a uniform or constant magnetic field is expressed by some parallel straight lines of uniform gap. Here you have many parallel straight lines in purple color. This represents the magnetic field lines. So the number of field lines passing through the coil is called the magnetic flux linked with the coil. Here, how many field lines are passing through the coil? 1, 2, 3, 4, 5. Right? All the field lines are passing through the coil. Can you see here?
Yes, we can see.
So that is maximum flux. So flux means the total number of field lines passing through the coil. If the flux is high, we will represent there more field lines. Here you can see the flux is more because there are more field lines. Here the flux is less. Why? There are less field lines. And here you can see a sheet kept like this. The coil is kept like this. Is there any magnetic field lines passing through the sheet here in second
One,
figure?
right?
Is there anything passing through that?
The last one is not with it.
No, I am asking about the second one. Here,
Acha.
can you see any field line passing through the coil?
No.
No. So the magnetic flux here is 0. So magnetic flux means the number of field lines passing through the coil. Flux is something that represents density. Suppose there is too much traffic, many cars are going through the road at the same time. Then we can tell that the flux, the traffic flux is too high. Suppose there is early morning around 4 a.m. There are no vehicles passing through the road. Suppose then the flux is 0. The traffic flux is 0. Is that clear to you? What is the meaning of flux? Flux means more things are going through that. Then we tell that the flux is high. Now, can you imagine what is flux? You should
Yes,
get a
teacher.
feel for flux.
Sir, but in the second figure, how is possible that no magnetic field is going through that coil?
Because it is
Because
kept like this. The field lines are all
at
going
least
like
one can also go, right?
hmm?
At least one can also go.
Not going through the coil. If the coil is like that, okay, everything will go. If the coil is kept like this, parallel to the field, nothing will go, right? It will not
I
go
mean, it
into
should go
the
from the
coil.
middle.
Yeah, it will not go into. Let me
Okay.
tell you. Suppose I have a ring and the water is flowing in a river. Suppose I have a ring and the water is going in a river. I just hold my ring in this way. This is the ring and the water is flowing in this direction. If I hold my ring like this, all the water coming will go through the ring, right? All the
Yes, got
water.
it.
So there is maximum flux. Now suppose I keep the ring like this, which is along the direction in which the water is flowing. Will the water flow through the ring?
No, it will go
No.
side.
So no flux is going through the ring. That is the difference. Is that clear now?
So the coil have, I mean, it has an resistance at the side of, I mean, no, nothing can go in from that side.
Yeah, if it is kept parallel, nothing is going into it.
Okay, okay, okay.
Suppose you want to take using a bucket water from a river. You have to hold it like this, right? You have to hold it like this and take the water. So more water will be collected inside the bucket. So maximum flux. Suppose you go and keep the bucket straight like this. Will it enter into the bucket? No.
No, no.
No. Right? Because the surface is parallel. That is the difference. So if you keep the, as here, there will be maximum flux if you keep with the area of the coil perpendicular to the magnetic field. Then the area vector is also perpendicular to the magnetic field as shown by A. So A and B are in the same direction. Theta will be 0, cos 0 is 1. So the magnetic flux is maximum, B into A. Suppose you keep it parallel to the magnetic field and the area vector is always perpendicular. So it is pointed up as shown in the figure. Therefore, the angle between area and magnetic field is 90 degree. Cos 90 is 0. So what is a flux? 0. If it is at any other angle, you have to take cos theta, where theta is the angle between the perpendicular area and the magnetic field. Is it clear to you what is magnetic flux?
Yes, teacher.
Yes. Yes,
Okay,
teacher.
so you have to remember that magnetic flux is a scalar quantity. It is defined as a product of the magnetic field and perpendicular area. Or in other words, in the form of formula, you can remember phi is equal to AB cos theta, where theta is the angle between the magnetic field and the area vector. And if theta is equal to 0, cos 0 is 1, the flux will be maximum. If theta is equal to 90 degree, cos 90 is 0, so the flux will be 0 minimum. Now, let us see the law of electromagnetic induction put forward by Michael Faraday. We'll be using this quantity phi in that formula. That's why we first discuss what is magnetic flux. So Faraday's laws of electromagnetic induction. As I told before, there are two laws. The first law says how electromagnetic induction occurs, or when a EMF and current is induced in a coil. We saw yesterday 3 experiments, remember? In those experiments, the deflection of the galvanometer shows the existence of electromotive force, which means EMF. At that time, voltage or potential difference was not a commonly used term. They use the word electromotive force, which means that makes the electrons travel and the current to flow. So EMF means voltage. So here the existence of electromotive force or electric current in the circuit is shown by the deflection of galvanometer in the experiments. This EMF is called the induced EMF, and this current is called the induced current. So we will be using the terms induced EMF and induced current. That is to show the current or EMF produced in the coil. How are they produced? One, we saw in the first experiment when you move the magnet. In the second experiment, we saw when a coil of wire carrying current, which means which is connected to a battery, if it is moved related to a stationary coil, then also current or EMF is induced. Third case, we saw that when the coil of wire connected to a battery is there, and when we just switch on and off, momentarily there is galvanometer deflection. So in all this case, the galvanometer deflection shows the existence of a electromotive force or electric current in that circuit. That EMF is called the induced EMF, and that current is called the induced current. So is that clear what is induced EMF and induced current? That is the newly produced EMF or newly produced current. Now, I just wanted to remind you of those experiments. Now, Faraday's first law states, whenever there is change in the magnetic flux passing through a closed coil, then an electromotive force or electric current is induced in the coil. Why we discussed electric magnetic flux before this? Because the term is used in the first law and also in the second law. So whenever there is change in the magnetic flux, what can cause change in the magnetic flux?
The plane we kept, I mean the coil.
Yeah, there should be change in the magnetic flux through the closed coil. So how can we produce change in the magnetic flux? Magnetic flux is equal to BA cos theta.
So changing the theta, I guess.
Yeah, by changing the theta means by rotating the area of the coil, right? By rotating. So theta, you can change and you can change the magnetic flux. Are there any other ways to change the magnet?
Yeah, it depends on the magnetic field and area also.
So if we change the magnetic field B, we can change the flux. Okay. So in all the three experiments, what we did was we changed B. By moving magnet in and out, we were changing the magnetic field near that coil. By moving a coil carrying current that produces a magnetic field in and out, we were changing B near the coil. Okay, so the magnetic flux change. So all these cases, we were changing B. There is also another way we can also change area, then also the magnetic flux will change. So whatever way we change the magnetic flux passing through a closed coil, then an electromotive force or electric current is induced in the coil. And the induced EMF or current exists as long as the magnetic flux changes. If it is not changing, which means if it is stationary, it's not changing. We saw that if the magnet remains stationary, flux is not changing. So there is no EMF or no induced current. Is that clear? Faraday's first law?
Yes,
Yes,
teacher.
teacher.
Yes.
Yeah. Now Faraday's second law states that the magnitude of the induced EMF. This shows how it is produced. This shows how much is produced. So the magnitude of induced EMF in a closed coil is directly proportional to the negative of the rate of change of magnetic flux passing through the coil. So negative of is not there. Okay. Let phi1 is the flux at an initial time. In the beginning, the flux was phi1. After some time t, let the flux was phi2. Then the rate of change of flux will be phi2 minus phi1 divided by time. Or if it is happening at a faster rate, we can tell it is d phi by dt. So according to Faraday's second law, the induced EMF represented by E or epsilon, sometimes you find it as E or sometimes in epsilon. In your textbook, epsilon is the symbol used. That's why I wrote here epsilon. It is directly proportional to the rate of change of flux. Epsilon is proportional to d phi by dt. Is that clear?
Yes.
So, according to Faraday's second law, you have to remember this formula. EMF is equal to d phi by dt. D phi means the change in flux. So you have to calculate the first flux and after
Teacher,
some time, what is the flux? Yes.
it was proportional, right? Then how it became equal
Equal.
without any?
Yeah. Without
There
any
wasn't.
because
Yeah.
if all these quantities, flux is expressed in Weber, that is the SI unit, and time is expressed in second, experimentally, the constant of proportionality was found to be 1. That is why the constant here, it's proportional. So there will be a constant, and it is found that the constant is 1. If 5 is expressed in Weber, that is the SI unit, and time is expressed in seconds, that is the SI unit. What is the SI unit of EMF?
Volt.
Volt. So if EMF is in volt, phi is in Weber, time is in seconds, then that constant's value is 1. So we can directly write EMF E is equal to d phi by dt. Now we saw this case for a single coil. Suppose there are more number of coils. If there are n coils, what is the equation? EMF is equal to n d phi by dt. Is that clear? So
Yes.
if they just ask you, state Faraday's law of electromagnetic induction, you have to mention both these laws. Whenever there is change in the magnetic flux passing through a closed coil, then an EMF or electric current is induced in the coil. And the induced EMF or current exists as long as the magnetic flux changes. And then the magnitude of induced EMF is directly proportional to the negative of the rate of change of magnetic flux passing through the coil. And you have to write this expression. EMF is equal to d phi by dt. So it also depends upon the number of turns. So one way to change the flux is change the number of turns. More turns means more EMF is produced. Is that clear? Is that clear? Okay. So in the next class, we will discuss the next law. And together, using the 3 laws, we will